All right, let's jump right into it. Today's deep dive is all about partially ordered sets, or posets for short. And since we know you're a PhD math student, we can skip right past the set theory 101.
Sounds good.
So what makes posets so special? They're like sets, but with a twist, right?
Yeah, you could say that. Posets are basically sets with a hierarchy, but it's a bit more relaxed than your typical strict order.
Relaxed hierarchy.
Think of it like a set with a relation. We often use the symbol S to denote this relation, and it tells us if one element precedes another. But here's the key difference. Not every pair of elements needs to be comparable.
Okay, so it's not like a straight line where everything has its place.
Exactly. That's where the impartially ordered sets comes into play.
So it's less about a strict ranking and more about dot relationships.
Precisely. Some elements are related, while others might be incomparable. Let's look at an example.
Hit me with it.
Take the power set of a set, say ABC. Remember, the power set is the set of all subsets.
Ah, power sets. Good times.
We can order these subsets by inclusion, meaning one set is less than another if it's a subset of the other.
So the empty set would be less than any other subset, right?
Exactly, because the empty set is a subset of every set. But now, how would you compare the sets A and B?
Neither is a subset of the other, so are they just incomparable?
Spot on. That's perfectly fine in a posit. This subset relation is a partial order because it meets three crucial conditions: reflexivity, antisymmetry, and transitivity.
Okay, break those down for me.
Reflexivity means an element is related to itself. Antisymmetry says that if A precedes B and B precedes A, then A and B are actually the same element. And transitivity means that if A precedes B and B precedes C, then A must also precede C.
Right, so those conditions ensure a sort of logical consistency in the relationships, right?
Precisely. Now, I know you're interested in how this applies to more advanced math.
That's where the real fun begins.
Let's move beyond basic sets and consider something like the divisibility of natural numbers. Instead of the usual less than or equal to, we'll say A precedes B if A divides B.
Interesting. So in this case, 1 would precede every other natural number.
Because 1 divides everything.
Yeah, exactly. But then, say, 2 and 3 would be incomparable.
Because neither divides the other. You're getting it. You're starting to see how posets offer a new perspective on familiar mathematical concepts. And this divisibility example gets really interesting when you start talking about maximal and minimal elements.
Because there's no greatest element in this poset, right? We can always find a bigger number.
True. But what about a least element?
Well, 1 would be the least element since it divides everything else.
Excellent observation. Now imagine trying to visualize this poset. Drawing all the relations between infinitely many numbers would be a nightmare.
Yeah, that's a recipe for a very messy whiteboard.
That's where Hasse diagrams come in.
Hasse diagrams, they're like a family tree for mathematical objects, right?
Yeah, exactly. In a Hasse diagram, we represent each element as a node, and we draw a line upwards from A to B only if A precedes B and there's no other element C in between.
Okay, so it's a way to streamline the visualization to get rid of the clutter and just show the essential order relationships.
You got it. And Hasse diagrams are great for identifying key features like maximal elements, minimal elements, chains, and antichains, which are sets of pairwise incomparable elements. They're a powerful tool for understanding a poset's structure.
I'm starting to see how posets can help us organize and analyze mathematical concepts in a really intuitive way. But you know me, I'm always looking for those deeper connections.
Of course. Well, let's take a look at how posets relate to the world of vector spaces, something you're probably quite familiar with.
Vector spaces. Bring it on.
The set of all subspaces of a given vector space actually forms a poset under the relation is a subspace of.
That makes sense. You can have subspaces nested within each other, but also subspaces that are completely unrelated.
Right. It's like those Russian nesting dolls, but with more complex relationships between them.
I love that analogy. So we can use posets to study the structure of vector spaces in a new way.
Exactly. And the subspace poset comes up in various areas of abstract algebra and functional analysis. But let's take it a step further. Have you ever encountered the concept of a lattice?
Lattices. I've definitely come across them in my abstract algebra courses, but I'll admit the connection to posets has always been a bit fuzzy for me.
Well, that's a perfect segue into our next topic. A lattice is a special kind of poset where every pair of elements has a least upper bound, called the join, and a greatest lower bound, called the meet.
So it's like taking a poset and adding this extra layer of structure where we can always find these optimal elements for any pair.
Exactly. And lattices have incredible applications in fields like logic, computer science, and even quantum mechanics. The whole new world waiting to be explored.
My mind is officially blown. I'm starting to see how posits can be a unifying framework for understanding these seemingly disparate areas of mathematics. But before we journey any further, I think we need a quick break to process all this awesomeness.
And we're back, diving deeper into the world of posits.
You were about to explain how lattices take posits to the next level with those joins and meets.
Right. Remember, a lattice is a posit where every pair of elements has a least upper bound and a greatest lower bound. The least upper bound of two elements, A and B, is denoted by AB, and it's called their join.
Join, got it.
It's basically the smallest element in the posit that's greater than or equal to both A and B.
So it's like finding the most efficient common ancestor in a family tree, the closest point where the lineages of A and B converge.
That's a great way to think about it. And the greatest lower bound is denoted by a B, and it's called the meet.
The meet, okay.
It's the largest element that's less than or equal to both A and B, like finding the most recent common descendant.
I see. It's like adding a grid system to our posit, making it easier to navigate and find specific points.
Exactly. Now, let's bring this back to your research. You mentioned working with algebraic structures, right?
Yeah, all the time.
Have you come across the concept of a sublattice?
Yeah, I have, but I've always struggled to visualize what a sublattice actually looks like within a larger lattice.
Well, a sublattice is just a subset of a lattice that's also a lattice under the same join and meet operations. Think of it as taking a section of the lattice that keeps the same grid structure with its own joins and meets.
Ah, so it's like zooming in on a particular region of the lattice, but preserving the relationships.
Exactly, and sublattices are really important for understanding the structure of lattices and how they can be applied. For instance, you might encounter sublattices when you're studying the ideals of a ring or the subgroups of a group.
Right, that makes sense. Now, you mentioned earlier that lattices have applications in logic and computer science. Can you give me an example?
Sure, in logic, lattices are used to model propositional logic. Each element in the lattice represents a proposition, and the join and meet operations correspond to the logical connectives or and.
So the lattice structure captures those relationships between different propositions based on their truth values.
Precisely. And in computer science, lattices are used in data analysis and program semantics. For example, in data analysis, you might use a lattice to represent different levels of detail in a data set.
So it's a way to organize and query information more efficiently.
Exactly. And in program semantics, lattices are used to model the different states of a program's execution.
Okay, so it helps to verify that the program is running correctly.
Right, it helps to both verify correctness and understand the program's behavior.
Wow, the applications are way more extensive than I originally thought. I'm really starting to appreciate the power and flexibility of posits and their extensions.
They really are remarkable. Now, let's switch gears a bit and discuss another important concept in the world of posits: order-preserving maps.
Okay, what are those? I'm intrigued.
An order-preserving map, also known as a monotone map, is a function between two posits that preserves the order relation.
So if A precedes B in one posit,
then the image of A under the map must precede the image of B in the other posit.
so it's like a transformation that keeps the hierarchy between the elements intact.
Exactly. Order-preserving maps are essential for comparing and relating different posits.
Because they show us how the structure of one posit is reflected in another.
You got it. And I bet you can guess where these maps have applications.
Let me think. Given our earlier conversation, I'm going to say category theory.
You're absolutely right. In category theory, order-preserving maps act like functors between posital categories. They let us map both the objects of the posits and the order relations between them.
This is all starting to feel very abstract, but I can see how it creates this powerful framework for understanding complex mathematical structures.
Exactly. The deeper you go into these abstract concepts, the more connections you'll start seeing between different areas of math.
My brain is definitely in overdrive right now. Maybe we should pause here for a moment before we go even further down the rabbit hole. Okay, I think I've caught my breath. We've journeyed through the basics of posits, explored their connection to lattices, and even touched on those fascinating order-preserving maps.
And how those maps play into category theory, too.
Exactly. Now, as we wrap up our posit adventure, I'm really curious about their practical applications. How are they actually used to solve problems in mathematics?
One area where posits really shine is in the study of combinatorial objects. Take, for example, the problem of counting the number of linear extensions of a given poset.
Linear extensions. Remind me what those are again?
Sure. A linear extension of a poset is just a way to arrange its elements in a total order that respects the original partial order. So you're basically taking those incomparable elements and giving them a specific order, but of course, without contradicting any of the existing relationships.
Okay. So you're creating a ranking of the elements that's consistent with the posit structure.
Exactly. And counting these linear extensions can be quite a challenge, especially for large, complex posets. But it's a problem with deep connections to other areas of combinatorics. It can really provide some insight into the poset's underlying structure.
That makes sense. It's like using posits to unlock the secrets of combinatorial objects.
Precisely. Another cool application is in topology. Remember those Hasse diagrams we talked about?
Yeah, the family trees for mathematical objects.
Well, we can actually use them to define some really interesting topological spaces.
Wait, so you're taking a visual representation of a posit and turning it into a geometric object?
Exactly. By considering the open sets of the poset as those that are upward closed in the Hasse diagram, we get a topology called the Alexandrov topology. And this connection between posets and topology opens up all sorts of possibilities for studying posets from a geometric point of view.
Wow, that's amazing. It seems like every time we dig deeper into posits, we uncover even more connections and applications.
And believe it or not, we've barely scratched the surface. Posets are used in all sorts of areas, like domain theory and computer science, and even the study of causal structures in physics. They truly are a fascinating and powerful tool.
I completely agree. As a PhD student myself, I'm walking away from this deep dive with a whole new appreciation for posits and how I can use them in my research.
That's fantastic to hear. Remember, this is just the beginning. The world of posits is vast and full of mysteries waiting to be explored. Embrace the elegance and power of these structures, and who knows what amazing insights you'll discover on your mathematical journey.
Couldn't have said it better myself. And for our listener, as you continue your studies, keep in mind that posits are more than just theoretical curiosities. They're a powerful lens for understanding the world around us, from the structure of algebraic objects to the nature of space and time. So keep exploring, keep questioning, and keep diving deep into the fascinating world of mathematics.